All right, well, technology, as you know, can be an absolutely wonderful thing, and at times it can be almost a curse. And I just spent about half hour, 40 minutes working on a video for you guys and realized that I hadn't taped some of it. It wasn't recording, and so I have to start over. All right, calm down. You're going to be all right. So my purpose in putting together this video presentation of the practice PARCC assessment is this is actually the only thing that we are given that we know these type of questions will be on the test. And so, as I told some of you before, there are some things that we just can't get to. The progression of geometry we cannot go fast enough to get to. And so as a result, I can actually give you some insight or a look into some of these problems, having not even taught them in class, with the hope that you'll be able to get these type of problems correct on your test, the first test. Now I will tell you this, the first phase is the non-calculator portion of the test. So you should be doing all this without a calculator. You know, some of you struggle doing mental math. Don't do mental math. Write it down on the paper. You should be able to figure things out, even if you have to write a whole bunch of 3s or 2s or 9s across the page and actually count. Do what you have to do to get these problems correct. Okay? Don't worry about time. If there is a problem that you absolutely have no idea what's occurring, skip it, move on to the next one, and then come back to it. Okay? All right, so as a result, taking a look here at the first one, some of these problems can be kind of wordy. Some of them use symbols, as opposed to actually giving you what's occurring within the problem. And this is a perfect example of that. This first one says the figure shows triangle ABC is what to DEF? Well, that means similar, okay? This little squiggle, it means similar to. Okay, so the two triangles are similar. Well, what does that mean? The characteristics of having similar triangles. Similar triangles. There are two of them. The first is that the corresponding sides are proportional. Okay, so as a result, you can set up a proportion to go ahead and solve for the unknown side lengths that are given. Okay, they have to be in the same ratio to each other. We oftentimes talk about similar triangle sides as having a scale factor to each other. And what I mean by that is this. If you look at the two figures up here, I think you can see that CB is the shortest side from this triangle, and that EF is definitely the shortest side from that triangle. So we can match those two sides up. They have to be proportional to each other or in the same ratio. If we match up the next smallest side, so AB would be the next largest side with ED, they're in the same ratio to each other. And so if I were to reduce 21 over 7, the scale factor for these two figures is in ratio of 3 to 1. Okay, and if I match up the longest sides with each other, you can see that the scale factor would be in ratio of 3 to 1, or you could say 1 to 3, whichever way you're looking at the scale factor of the two similar figures. Give me 1 second here. Sorry about that. I had to go back and make sure that my receiver was on. Now I'm paranoid that I'm not recording everything that I should record. The second thing that similar triangles have to have in common are that their corresponding angles are congruent. Okay? And so you can also look up here at the similarity statement, okay, and match up the angles. So angle A and angle D have to be the same measure. A has to be congruent to B. B has to be congruent to E. Okay, and F and C have to be congruent. Okay, and I think that you see that. You could also match up the corresponding sides with the similarity statement AB and DE. And in fact, that's what I would do. I wouldn't just look at the figure, because you can mistake BC and AB. I mean, they may not draw them proportionally. You have to look at the similarity statement. So that's what I would do. So how do you go about solving for x? That's what we're trying to do here. It says, what's the value of x? I'm going to go ahead and choose two of the sides. So again, I'm going to choose AB and DE. AB is 21, DE is 7. If I set that up, 21 over 7, and I match up, I come back to the original. I'm going to go with BC because I need to go ahead and figure out what that length is going to be. And if we look here, BC and EF correspond, so EF is a length of 5, and that would be one proportion we could use to solve for x. Another proportion you could use, if I start with AC, AC you see is the longest, which is 27. Okay. AC would correspond with DF, which is 9. And then I come back here, x is to 5, just like we did on the previous one. Okay. Either one of these proportions solved will give you the correct answer. If you cross multiply, 7x, that will be 105. Now again, if you have to, write it out longhand. Some of you use that lattice method, I think. I'm not as familiar with it, but when I would do multiply, here's what I would do. 5 times 1, 5 times 2 is 10. 105 is my answer there. Okay. And then from there, dividing both sides by 7. If you're not sure how to divide, you're going to want to look up long division online because, again, this is a non-calculator portion of the test. How I do long division, I ask myself, does 7 go into 1? No, 1's too small. So then I go, does 7 go into 10? Well, it does one time. 7 times 1 is 7. And there are 3 left over. Okay, so it's 7 times 1 is smaller than 10, but I want something that at least is equal to or a little bit less than the number I'm dividing into. From there, does 7 go into 3? No, it does not. So I bring down the 5. Does 7 go into 35? It does. 5 times. 5 times 7 is 35. There's nothing left over, so my answer is going to be 15. Okay. Going to the other one, just to make sure that we can do this correctly. 9 times x is 9x. 5 times 27. Again, I usually put the larger number on top. Okay, 5 times 7 is 35. Now the 3 I have to carry over. 10 plus 3 is 15. 13, sorry. I knew I did something wrong there. So we have 135. Okay, and then I have to divide both sides by 9. Okay, so does 9 go into 1? No, it does not. 9 go into 13. It does one time. So 9 times 1 is 9. I subtract that to get the difference. I get 4. And then the 5 is going to come straight down. Does 9 go into 45? It does 15 times. 9 times 5 is 45. There is no remainder left over. So my answer again is going to be 15. Okay? And so it's very, very important. This is a very simple problem. Get the ones that are simple right. Okay, the complex ones, you know, I understand those can be kind of difficult, but get the ones that you know how to do correctly. And again, no calculator allowed on this first section of the test. All right. Okay. Number 2 has to do with transformations. Let me just read it here real quickly. The figure shows 2 perpendicular lines, S and R, intersecting at point P on the interior of the trapezoid. Line R is parallel to the bases, so this one is parallel to the bases. The terminology you need to know for this is a trapezoid, so these will be the bases, and these 2 non-parallel sides will be the legs. Okay? So line R is parallel to the bases, these 2 bases here, and bisects both legs. So this length here and this length here will be the same. And it looks like an isosceles trapezoid. I'm not going to go that far, so I'll just say that those 2 lengths are the exact same. And line S bisects both bases of the trapezoid. So what that means is that this line cuts this segment in half, and this line cuts this segment in half. Now what does all that tell us? Well, it basically tells us that this point P right here is the center of this trapezoid. A lot to, to mark down to just say, hey, point P is the center of that trapezoid, but they're trying to get you to understand that point P is the center of that trapezoid. So, which transformations will always carry onto itself? Now, what that means is this. When it says carry onto itself, it's going to be the same position and congruent. This trapezoid up here is going to just be on the exact same position and congruent to itself. So same position and congruent to itself. You might want to say it's the exact same image, okay? That's what we want to know. Which of these transformations will allow us to say that. So I'm going to go ahead and redraw all, well, there are 5 of them right there, starting with letter A, is a reflection across line R. So if I have the original image, now let me pause for 1 second. If I were you, if you struggle with doing these, not so much the reflections, I think those are probably pretty easy for most people to understand. It's the rotations that can be kind of hard. I would encourage you to ask your proctor, whoever's giving the test, if you can have a set of scissors to cut out a trapezoidal image. All right? If they won't allow you or say that's not allowed, go ahead and take a piece of your test and rip out an image that looks like the trapezoid that we have here, and I'll show you why in just a second. So if we're reflecting across line R, here's the original image. Okay? Across line R, what that means is that this length here is going to be equal but in the opposite direction. So I'm going to drop it down. That point will be right there. This point, equal but in the opposite right there. Equal but in the opposite will be up here. Equal but in the opposite up here. So the new image is right there. Now, is that the exact same? Is it mapped right back onto the original image? And it's not. So as a result, point A is not a possible answer for this problem. For point B, we're going to reflect across line S. All right, so here's what we have. Okay, equal but in the opposite. So that point goes there. Equal but in the opposite, that point goes there. Equal but in the opposite, that point goes there. Equal but in the opposite, that point goes there. As you can see, if I connect all 4 of those points, they are mapping right back onto the original image. So point B is one of the answers for this problem. Again, it's a select all that apply. Make sure you work through all parts of the problem. Letter C says a 90 degrees clockwise rotation. Now, clockwise, I'm going to go ahead and just do, if we were to start here, actually we'll start at 12 o'clock. Clockwise means to go to your right, just like the hands on the clock. If you kind of have a brain fart while you're taking the test, look up at the clock in the room. Ask yourself, what direction are the hands moving? That's what you need to put down as far as the clockwise rotation. Obviously counterclockwise, and it's very important to pay attention to which way we're rotating the figure, because that will change what the eventual image will be. It's going to be in 9 degrees counterclockwise, going the opposite direction of the hands of the clock would be counterclockwise. So letter C, we are looking at a trapezoid that's being rotated clockwise about point P, 90 degrees. Now, 90 degrees, I don't have to be real specific when I rotate this 90 degrees. I don't have to know the ordered pair of where any of those points lie. I just have to know what a 90 degree rotation is going to look like. And so if I was to put my hand on this image and rotate every part of it 90 degrees, basically every part just goes into the next quadrant, okay? And so this point is going to rotate. It'll probably come down here somewhere. This point will rotate. It'll come down here somewhere. This point rotates, comes up here somewhere. And then this point rotates and comes over here, okay? So as a result, should be up in there actually. That's the new image, 90 degrees counter or clockwise. Is it mapped onto the original image? No, it's not. So as a result, this is not a possible answer for the problem. 180 degrees for letter D. If I go ahead and draw the original image again. Okay. 180 degrees means that it goes from, for example, if I have my 4 quadrants here. Oh, not 4, sorry. 3, and then 4, okay. It's going to go to the opposite quadrant. And so as I look at this, this is in quadrant number 3, so it goes to quadrant number 1. It'll probably be somewhere up in here. This one goes from quadrant number 4 to quadrant number 2, somewhere up in here. Okay, quadrant number 1 down to number 3, somewhere down in here, somewhere down in here. Okay, and I may have put those a little high up in there, but what I want you to see, or what I want you to be able to see as we look at this, is that it probably should have went across here. That's probably where it should have been, not as high up there. All right, but it's basically the flip of the figure across the line R, which we've already said is not possible. So this one again is not possible. The rotation 270 degrees clockwise, it's important that you understand the degrees as we look at this. If I start here, this would be 90 degrees, 180 degrees. This would be 270 degrees. Each quadrant is 90 degrees, so adding those together we get 270. So if I look at point E, or answering the letter E, and I go ahead and draw that figure out, we're looking at something like this. Okay? 270 degrees clockwise. And so if it's 90 degrees, this one goes up here. Okay? If it's 180 degrees, it goes over here. 270 degrees, it goes down here. Okay? This one, if I was to do 270 degrees, 90, 180, 270. So it will be somewhere up in here. Okay? 90, 180, 270, 90, 180, 270. Okay, this one I probably should have marked down here. Okay, but what I want you to see as you rotate that is that the image is not mapped directly back onto the original image. And so again, make things easier on yourself. If you're struggling with the rotations, obviously not an answer, struggling with the rotations, cut out a figure, place it on there and rotate it with your hand, okay? Just make sure that you're rotating it the correct direction, okay, whether it's clockwise or counterclockwise. But I think 90, 270, just turn it a whole quadrant from wherever it's going to be. 180, I think you'll get that one correct. So, all right, question number 3 says this. The circle with center F is divided into sectors. Now, just reminding you, sectors are sections of a circle. And so, as I highlight this, this would be one sector. This would be another sector. This would be another sector. There's lots of sectors of circle up there. So, sections of a circle. Okay. In circle F, EB is a diameter. Okay, so it's important to know that. EB is a diameter, which makes this 180, makes this 180 as well. And FB is 3 units. Now, what I would do on my test is highlight that FB is a radius. Make sure I make that clear to myself as I'm working through these problems, what that is exactly. Select the correct expression that represents the arc length of arc AED. Okay, now first of all, each of you, given the paper pencil test, should be given a formula sheet. On that formula sheet is going to be the arc length formula. Now that arc length formula is going to be this. It's going to be the arc measure over 360 times pi times diameter. Basically what it is it's a portion of the entire circle. And so, again, that's the formula right there. Now, if the term arc measure is unfamiliar to you, let's see here. Arc measure, A-S-U-R-E, is equal to the central angle measurement. Okay, the arc measure is equal to the central angle. So what I mean by that is this. The measure of this arc right here, not the length, but the measure is 120 degrees, equal to the central angle measurement right there. So, if I need to figure out the arc measure of arc AED, this arc right here, I need to figure out, first of all, what the measure of this central angle is going to be. Now, the measure of this central angle can be found by taking, if this is 120 and this is a diameter, it's 180, 180 minus 120 gives you the leftover angle measurement there. Likewise, if this is 180 and these two angles together make 75, 180 minus 75 gives you the central angle measurement, so it's 105. So the whole arc measure of arc AED is 165 degrees. Now I'm going to go ahead and put that in down there, 165 over 360 times pi, and don't you dare put 3 as the diameter, okay? Again, I'm going back to what I'm reading in the problem, radius, okay? So as a result, my diameter is going to equal 6 units. So I plug in 6 down here, okay? Now the first thing I would probably do, again, this is a non-calculator test, I'm going to go ahead and divide 165 and 360 by the same number. Now the largest number that I know that goes into both those, I know is going to be 5. There may be a bigger one, but that's the one I'm going to start with. So if I go ahead and take 5 into 165, I can say, okay, how many times does 5 go into 16? Because it doesn't go into 1 evenly. It's going to go 3 times. 3 times 5 is 15. How many times does 5 go into 15? Again, because I brought down the 5. 5 goes into 15 3 times. 3 times 5 is 15. There is no remainder left over. My numerator reduces to 33. Now I have to do the same thing to the denominator, so how many times does 5 go into 360? Well, 5 doesn't go into 3, but it does go into 36 7 times, because 7 times 5 is 35. Now there's 1 left over. 5 can't go into 1, but 5 can go into 10 2 times. 2 times 5 is going to be 10. There's no remainder, so 72 is going to be my denominator. Now, to finish this problem off, again, it doesn't look like anything we have over here as far as our possible answers. I'm going to rewrite this a little bit differently. I'm going to do 33 times pi times 6 over 72. Okay? Now, the reason I'm doing that is because I see 6 and 72. Well, I know 6 goes into 72 times evenly, 72 evenly. So if I do that, 6 goes into 72, 6 goes into 7 one time. 1 times 6 is 6. 1 left over, the 2 comes down. 6 goes into 12 twice. 2 times 6 is 12. There's no remainder, so as a result, I can reduce this 6/72 down to 1/12. Okay? Now, if I simplify that, here's what I have. 33 pi. I don't have to write down the 1 because 1's always present, over 12. I look over here, again, I don't have an answer. But I see 33, I see 12. 3 goes into both those evenly. I know 3 goes into 33 11 times. And 3 goes into 12 4 times. And now, all of a sudden the answer becomes so much clearer. Okay? So again, we're really testing, can you multiply and can you divide without using your calculator right there? I think that's a great problem. Again, it's one that's very easily gotten as long as you can place everything correctly within the formula and then simplify that formula. Okay, now I'm going to be honest. When I got to number 4, when I was taking this test myself, just to make sure I knew all the ins and outs of every single problem, number 4 was one of the questions I got to. I was like, what is this talking about? Okay, and as I began to break down every single part of it, it became very clear. So this is a very attainable problem if you have a problem like this on the test. Here's what it says. A rectangle will be rotated 360 degrees about a line which contains the point of intersection of its diagonals and is parallel to a side. What three-dimensional shape will be created as a result of the rotation? Well, here's what I want you to see. I'm going to draw a rectangle onto the coordinate plane and then break down the sentences as it says. 360 degree rotation. What I want you to know about this is whenever we have a 360 degree rotation, you are looking for an object that is circular in nature. Object circular in nature. Okay. What I mean in nature, there's got to be some circles present. Okay. So as of right now, I know the cube and the rectangular prism are not viable options for this type of problem. From there, it says about a line, so we're rotating about this line that contains the point of intersections of its diagonals. If I go ahead and draw on the diagonals, the point of intersection is this center point right there, okay? So we're rotating it about that point and is parallel to a side. Now, this point is parallel to these sides. It's also parallel to these sides. So there's one of two ways we can rotate this figure, but it ends up being the same in both rotations. So if I was to rotate it parallel to this side, it would look like this. Now I know I'm not the best artist there, and I did this bottom part kind of quickly. I should have kept it out here a little bit. Okay, but what I want you to see, I hope you see this cylinder right here. That's the figure that we're looking for. Okay, so cylinder is the answer. If I were to do it the other way, okay, remembering that this point is also parallel to these two sides here, I could go ahead and rotate it 360 degrees that way. And I hope again you see that it's going to be a cylinder. It does have a different orientation as far as the radius and the height of the cylinder, but it's still a cylinder in nature. Now, when could it be a sphere? If I was to take a half circle here and rotate it, let's say across the y-axis, 360 degrees. Now, mirror image on the other side, and then, okay, so again, I know I'm a bad artist there, but hopefully you see that that sphere is formed by that half circle being rotated. So, again, a problem that you can get right if you break down the wording of the problem correctly. Okay, number 5 is actually a problem that if you do this problem online, it does give you coordinate plane paper. The one that from the text, the paper pencil test, doesn't seem to give you graph paper. So I'm kind of frustrated with that, and I'm going to try to supply all of the geometry classrooms with geometry paper like we have in class so that you can work out a problem like this. It's a lot easier when you can see that problem being worked out. So here's what we're given in number 5. Line segment JK in the XY coordinate plane has endpoints with coordinates negative 4, 11. Okay, I'm going to graph that first. 1, 2, 3, 4, and then this is 10, so that'll be 11. I know it's off the graph, but I can actually just use that right there. And then 8, negative 1. 1, 2, 3, 4, 5, 6, 7, 8, negative 1. Okay. What are 2 possible locations for M so that it divides JK into 2 parts with lengths of ratios 1 to 3? Now, this whole problem hinges on your understanding of ratios. Okay? And so, what I want you to see from this problem is this. If we want to break up this segment into ratios 1 to 3, how many total segment lengths do we have present? Well, there are 1 on one side, 1 on this side, and 3 on this side, so there's a total of 4 segments present. Okay? And so this segment here, in order for it to be 3 times the length of this segment here, we have to have 4 total segments present. Now, if that doesn't make complete sense to you, keep paying attention. I think it will in just a second. So in order to figure out how to break this segment up into a ratio of 1 to 3, let's see here, there it is. I'm going to go ahead and drop it so I can measure the rise of my, get that out a little further. I can measure the rise of my segment, and I can measure the run of my segment. Okay? So the rise, this is 1 here, there's 10 there, that's 11, 12, okay? And there are 4 here on this side, and there are 8 here on this side, so a length of 12. Again, you can just count that if you just go across there. Don't forget to start at 0 and move your way to the other line. Now, if I'm going to try to figure out where this segment's going to divide, this point's going to divide the segment in the ratios 1 to 3, I'm going to divide both the rise and the run by the total number of segments that we have present. So if I divide 12 by 4, I get 3. 1, 2, 3, make a point. Divide the run by 4, I get 3. And this point here, 1, 2, 3, 4, 5, up 2, 5, 2. is the location of one of the points that's going to break that segment up in the ratios 1 to 3. If I do the same thing from the other endpoints perspective, divide the 1, 2, there. The rise by 4, you get 3, 1, right there. And this is negative 1, 1, 2, 3, 4, 5, 6, 7, 8. Is that present? Negative 1, 8 is present. Awesome. Okay. Now, I would like to prove to you guys how this breaks the segment up into ratios 1 to 3. And in order to do that, I'm going to use my Pythagorean theorem right here with this right triangle right here. Now this length obviously was 3. This length was 3. It's a 45, 45, 90 triangle. If you work it out using the Pythagorean theorem, you get 9 and 9 make 18, the square root of 18. Or, as we've talked about with the 45, 45, 90 triangles, 3 radical 2. Okay? Now, if I do the same thing with the other segment, this length right here, this being 3 and this being 12, that means that this length has to be 9. You can also just count it if you want to. That's fine as well. You can count this length as well. Make sure you go all the way over to here. If you do that, this length will also be 9. And so 9 squared plus 9 squared would be 162. And the square root of that length is what we're going to have. Now, we also know that this is a 45, 45, 90 triangle. So I can write down 9 radical 2. Okay. Now, I do want to compare those two lengths to see if they are in ratio of 1 to 3. So 3 radical 2, is that in ratio of 1 to 3 with 9 radical 2? Well, remember, we can write ratios like fractions, just like that, and I can cancel out the like terms. And so if I reduce the fraction 3/9 to 1/3 and rewrite it as a ratio, we do have it in ratios of 1 to 3. Now I can do it from the other endpoints perspective to get that other end value, but I think I've proven that enough there. So those are the 2 points that we're looking for on that problem. Okay, so this is actually the problem I messed up on the last time when I was making up this video, but this problem actually kind of frustrates me because it covers 2 concepts. One concept isn't covered to the end of geometry in the progression of our textbook, and so I'm having to move some things around just so that we get it in before the phase 1 test. The other concept isn't covered until Algebra 2 within our curriculum, and so we've got to continue to evaluate when we teach things and try to get this in before phase 1. But it's not earth-shattering things that are covered here. Hopefully you'll catch on as we go about doing this problem. Again, I would review it if I get going too fast. So here's what I want you to see. It says use the information provided in Part A and Part B for question number 6. The equation is this: x squared plus y squared minus 4x plus 2y equals b describes a circle. Whew, that's a lot. Well, first thing I want you to know about this is, what is the circle equation? Okay, circle equation. If I was to graph this within the coordinate plane, how would I do that? Well, here's the equation. X minus h squared plus y minus k squared is equal to the radius squared. That looks like a lot, but it's actually really simple in the fact that the center of our circle is always going to be at h comma k. Now I want you to realize this, that h is the opposite of the h that's up here, because the h that's up there is negative h. Okay, so you make it the opposite when it comes down into the ordered pair. The k that's up here is brought down here, but it's the opposite k. And so the center is always at hk, and obviously the radius of the circle, if you were to graph it within the coordinate plane, is just going to be the r value, which means you're going to have to square root the radius squared, whatever that is. So the first part is to determine the y-coordinate of the center of the circle. How do we do that? Well, we're trying to find this k right here, that y value, that y-coordinate. And what I'm going to do is I'm going to order this equation, so I'm going to group all the like terms. But in order to figure out the y value over here, we have to do what's called completing the square. Completing the square. Okay. So as we take a look here, I'm going to go ahead and write down x squared minus 4x and I'm going to leave a blank, plus y squared plus 2y, I'm going to leave a blank, is equal to b. Okay? Now the reason I'm leaving the blanks there is because we have to figure out what goes inside of those blanks when we don't have that third term in order to figure out. So how do we figure out this third term? Well, within a trinomial, we can list these as a, b, and c. If you remember when we did the quadratic formula, we listed those as both a, b, and c. And so as a result, in order to figure out what c is going to be, well, let me finish this up. Likewise, this will be a, this will be b, and this will be c. So in order to figure out the c, when you have to complete the square, you're going to take b over 2 and you're going to square it. That value will allow you to complete the square, which gives you a factorable trinomial. And so if I do that with this first one here, negative 4 over 2, and I square that, this gives you negative 2 squared gives me a positive 4. All right, now if I add 4 to one side, I have to add 4 to the other side, so I'm just going to do that right there. If I take the b for the second trinomial that we're working with, this trinomial here, taking this b right here, if I take 2, divide it by 2, and then square it, that's 1 squared is just 1. So I'm going to add 1, and I'm going to add 1 to the other side. Okay? Now, we still want to get our equation, this equation over here, back to looking like something like this so we can figure out what the h and the k are going to be, the center points x and y. In order to do that, I'm going to write it down like this. For the x values, this part right here, okay, what are the factors of x squared? Well, it'll be x and x, so x squared. So I'm going to put x right there. What are the factors of 4? Well, 2 times 2 is 4. And since the middle term is negative, I'm going to put minus 2 right there. Now, how do you check to make sure that that's the correct, that I've done all that correctly? Well, I can actually go ahead and FOIL the factor of x minus 2 squared, and it should give me what we have originally up in here. Okay? And so as a result, if I do that, foiling this, x squared, the outer terms minus 2x, the inner terms negative 2x, and the last terms positive 4, that gives me x squared minus 4x plus 4, and if we look over here, we've got the exact same expression up there, so I know I've factored it correctly right there. Factoring out the second portion, the y's, I know that the factors of y squared will be y times y squared. The factors of 1, well, there's just 1. It's going to be 1. And this middle term is a positive, so I'm going to put a plus right there. So, to check myself on that one, y plus 1, y plus 1. The first terms are y squared. The outer terms plus 1y. Inner terms plus 1y. The last terms plus 1. If we combine the like terms here, y squared plus 2y plus 1, we get the exact same expression that's up here. Okay? And then what's left over is actually b plus 5. Okay? So what's the center of the circle over here? Well, the center is going to be at the opposite of this value and the opposite of this value. Okay? So our answer for this one right here is going to be negative 1. Okay, that's what we're looking for there. For the radius, part B says this. The radius of the circle is 7 units. What's the value of b in the equation? Enter your answer in the box. Well, if the radius is 7, I'm going to plug 7 into that right there. So if I take 7 squared, I get 49. Now I know that this right here has to be equal to this over here. So if I set those equal to each other, b plus 5, I'm going to subtract 5 from both sides of my equation, and 44 is the value that I would need to substitute in for b so that my radius is going to be 7. Okay? Now I realize that was a lot of involvement right there, but again, it's not highly complicated, and so if you need some other practice problems on that type of problem right there, come see me, and we'll try to set you up. So. All right, and we've come to the end here. Number 7, in the xy coordinate plane, triangle ABC has vertices A, which is at 1, -2, B, 1, and then 0.5, and C, which is at 2, 1. DEF has vertices D, 4, -3, E, 4, 2, and F, 6, 3. The triangles are similar because DEF is the image of ABC under a dilation. What is the center and the scale factor of the dilation? All right, now, for this one, again, I would make sure I have some graph paper. It doesn't seem like there was any graph paper present, but I will try to make sure that's going to be present in all of your classrooms when you take the test. But here's what I would do. Just to make sure I'm accurate, well, let's just leave it at what it is. I was going to make each grid mark worth a half so that we can make sure that we are on the right part, but then that gets us off the graph here. So let's just go ahead and set it where it's going to be, and I'm going to graph the first 3 points. And so the first point is at 1, -2, so 1, -2. That's point A. Point B is at 1 and then 0.5. So there's point B. So A, B, and C is at 2, 1, is that right? Move this over. C is at 2, 1. So if I do that over 2, 1, 2, up 1, right there. Okay? You know what? I think I am going to make it on a... Every point's going to be on the half. So this will be half, this will be 1, half, 2, half, 3, half, 4. Now if I do that, it's going to be huge, isn't it? All right, reset. Okay. All right, so this is going to be C. And I'm going to connect all 3 of those points. Okay, now remember, you've watched some videos on dilations. Dilations, it's going to be either bigger or smaller than that, and we're going to try to figure that out. So D is going to be at 4, -3. 1, 2, 3, 4. 1, 2, 3. Okay. E is going to be at 4, 2. 1, 2. And F is going to be at 6, 3. 4, 5, 6, 1, 2, 3. Okay. So the dilation, let's make sure we're reading this correctly here. It says the triangles are similar because triangle DEF is the image of triangle ABC under a dilation. What is the center and scale factor of the dilation? Select the true. So here's the key to the problem when you're talking about scale factor. We're going from the triangles are similar because DEF is the image of triangle ABC under what dilation? So we're going from ABC to DEF. So as I look at the 2 images there, ABC is increasing in size to get to DEF. So I know that it's got to be greater than 1. So I know that D cannot be an answer there. Okay, it's got to be greater than 1. It's getting larger. Now from there, the easiest way to figure out what the scale factor is just compare 2 of the corresponding sides. This side here corresponds with this one. If I count this, that's 3. Counting this one, 1, 2, 3, 4. Hold on. 1, 2, sorry. 1, 2, and then a half. It's a half length right there. 1, 2, 3, 4, 5. So 2.5 to 5. I am doubling that length right there. And so it's 2 times as large. E is going to be your answer, one of your answers. It's not 4 times as large, it's just 2 times as large. Now the center of dilation, I think the easiest way to find it, and again, I think that you guys should be given a ruler or something to guide you in this, but you want to go ahead and connect the 2 points that you were given the graph, the corresponding points. And if I go ahead and do that, right there is 1. If I go over here and do this one, again, I'm trying to graph or connect the 2 points right on where they're at. So if I go here, connecting F to C, okay. Now you'll notice that I guess this is up 1 over 2, up a half over 1. The slope is the same, so all 4 of those points are going to remain on the same line. So this is the center of dilation there. When you connect the corresponding points and connect the corresponding points, they should lead you back to the center of dilation. So that would be -2, -1. And as we look up here, do we have that? Yes, we do. And that's the center of dilation there. All right, so hopefully this was an informative tutorial on how to do each of the problems there. If you have other questions or you want to see some other examples, we can always think up some new ones for you. But the key, again, in any standardized test, any test like this, is to get all the problems that you know how to do correct, and any of the ones that you don't know how to do, give your best effort on. And so I appreciate your time and attention, and good luck on your PARCC assessment.